quick recap of we really didn't do anything that big on 16.1, our last chapter. We're looking at vector fields, also called vector functions. And these are interesting because it's a function, but the answer is not a scalar, a single object, but a vector. And this might be one of the ways in which you would describe it. You put a big arrow above it, but in the textbooks it's bold. So this would be a vector field, which is another name for a vector function. The vector field F, capital F, is made up of three components, an X, a Y, and a Z component. Each of these components can, and very often do, have X, Y's, and Z's in it. So it is possible for you to have a vector field says 42. That looks like that, right? Any one of the three components could be a number on its own. Any one of the three components could have X, Y, and Z in it. It really doesn't matter. Any given function you can think of X, Y's, and Z's can go here, and they're all independent typically. Now we've got another guy called the gradient, well, its full title, but nobody uses it, is the gradient vector field of the vector function, of the function, not the vector function. So the gradient vector field of the function. So this is a normal function, you know, like x squared plus y, right? Just a single function of x, y, and z is given by this. It's a upturned triangle f. So that means this is a vector. And you get the vector by taking this function and partial derivative with x, partial derivative with y, partial derivative with z. And normally we just call that the grad of f, or I've seen it sometimes called, delta f. So if you're saying out loud, you'd say delta f is, or grad of f is. It's very often called, well, it's called all sorts of things apart from grad and delta. I've also heard it called the gradient vector, which is just another name for the same thing. So what on earth is it? Well, I can show you in 2D. I wouldn't want to even try and show you in 3D. In 2 dimensions, you've got a function z equals f of x, y, right? So it could be, you know, the hill, like this. Now, what you get when you get to the grad of f is this vector. Now, you notice this is a 2-dimensional vector, yet the surface of z, right, is a 3-dimensional surface. So that's a little bit weird, but that's what it is. So you take this guy and you choose any point on the bottom. Can you imagine some point here, P, with coordinates x, y? Now, if you go up, it hits the surface. I'll call it Q. This vector, if you imagine it in flat to the surface, this is what gradient f looks like. It's a vector that is flat, horizontal, on the surface of the shape. So can you imagine that any given point on this surface, you might get a flat one going this way, and over here you might get a flat one going this way, and over here you got a flat one going this way. And what actually are these darn things? Well, if you do contour maps, do you know the ones where you take a surface and you slice it like it was a hill, and you slice it at points of equal height, right? A contour map. If this was the point P, the gradient would be at right angles to that contour line that P is on. Now, I don't know if any of that helps you visualize what you're getting, but that's what a gradient vector does. I keep hesitating. No, my brain's not working very well today. And I keep correcting myself, so I'm going to stop doing it. If I say gradient vector or gradient field or gradient, will you just assume that I'm talking about the same thing all the time? So I don't have to keep saying, well, you could also call it this, or you could also call it that. So we get the gradient and off we go. Now, we did it last time, but I just want to show you one more example before I move on. The first part of your homework is basically using the software and finding out what these vector fields, vector functions look like. Are you looking hopefully at GeoBra? Is that what you're saying?
Mm-hmm.
Okay, we're good then. So what you're looking over here is, zoom this up a little bit, is capital F. So we're back to vector fields here. Sine X, sine Y, cos Z. Now, there's no reason in the world why this should just have X's, Y's, and Z's, but I picked them. And if you put this in, do you see what this looks like? It's quite a messy looking thing. In this particular case, at any given point X, Y, Z, there is a vector associated with it. Now, if you rotate these, you suddenly see structure. So it's not uncommon for what looks like, well, I can't call it random, but chaotic, at least, that a chaotic vector field may not be as chaotic as you think. If I rotate it this way, can you see that from the center there's a kind of going outwards, at least in one of the planes? And if you look at it side on, that's about it. Can you see there's a kind of upwards, downwards, or a kind of flow from the top and a flow from the bottom? So what you're seeing here is quite a complicated three-dimensional movement of air or magnetic field or whatever it is, flux, all sorts of cool stuff. So it's a really cool model. Vector functions allow you to model quite dynamic and intricate situations. So they're kind of fun for that. Okay, so bread and butter stuff. Let's do some bread and butter stuff. The things that you're going to spend most of your time doing in this section is simply just calculating the gradient of f. So we're back to doing gradients of a function. So let me find one. This is like question 7. The good old-fashioned function, it's a 2D, well actually it's a 3D function because of it's a surface. Looks something like this. And you're going to be asked to find that guy. Okay. I like this notation, so that's the one I'm going to choose. Pardon. Can you see anything I'm writing down?
No.
You know you're meant to tell me when I do this. You were just going to let me rant on for 20 minutes and then casually say, I didn't see any of that. Okay. So here is the function. We're going to find this guy. So as long as you're up to speed on partial differentiation, this should be good. It depends on what you've got, what you're going to do. And that seems a bit vague, but would you agree that if you're going to do this with respect to y, it's not too difficult? But if you're going to do this with respect to x, there's a little bit more work. So let's do this one first. If you differentiate this fella with respect to y, you will get ex to the 2xy times something else. Won't you get something extra? What extra will you get?
2x.
2x.
So are you all happy about where the 2x squared came from? Now, this fella here is essentially a product rule, isn't it? Because it's an x times e to the 2xy. Both pieces have an x in it. So think, so it's f dash j plus f of g dashed, where I think this is f, and I'm going to think of that as a g. So let's see what we get. You're going to get 1 times leave this guy alone, plus leave this guy alone, and differentiate this guy with respect to x, which is going to get you e to the 2xy. But with respect to x, you then get an extra times 2y. Are we happy about where that came from then? Partial derivative with x, comma, partial derivative with y. It's called the gradient function. Quite an interesting function, vector function. Used in all sorts of weird ways that you wouldn't naturally expect. Next fella is the dreaded square roots. They love square roots. This particular function, at least the version I'm doing, this one, and it's very similar to question 8. If you think this is essentially a fourth dimensional function, because there's 3 variables in that one, so I could have called this w equals that, right? So they're really 4 dimensions. So don't try and draw it. It wouldn't be a good idea. But do you recognize this as being the distance from the origin? So this function is basically at any given point in 3 dimensions. Can you imagine in 3D you had a dot, and in that dot it had a number associated with it, and that number was how far away it was from the origin. So that's maybe one way of trying to visualize what that is in 4D, right? You've got all the points in 3D space, but every single one of them has got a little number stuck to it, right? A little imaginary number that if you looked, you could see. And it happens to be the distance from the origin. Now, if I'm going to do the grad of f, which we are, which means I'm going to do this guy, I'm going to do this guy, and I'm going to do this guy. What, this question's a bit vague, but I don't want to give too much away by being too clear. What trick are we going to use to reduce our workload?
Symmetry, right?
Yes, good. It wasn't that weird a question. Now, would you agree that in this function, it is symmetric? So when I get the answer to x, or say this one, shouldn't I be able to predict these two without doing it, right? Without physically going through the same process. Of course, I will have to call this guy x squared plus y squared plus z squared to the power of half, right? Because you're going to have to differentiate, you need fractional powers. So let's just find this fella. So with respect to x, you get 1/2 x squared plus y squared plus z squared, reduce the power by 1, and then the derivative of what's inside with respect to x. Then still points, 2, and that cancels, that x is good. This guy goes downstairs. And then to complete the style points, return the question to what it looked like originally, which means I can now do the gradient. It's x over this fella. Then somebody else, and then somebody else. Okay, what would the middle term be using symmetry?
Y on the numerator.
Would you agree z for the third one? Don't need to know it for this question, but there are a couple of things that you might choose to do. You might write it like this. Would you agree that's equivalent? You might also notice that this is true. This vector, this gradient of f, this particular one, this isn't true, but all of them, just this one is true. Isn't it a unit vector? Agreed? How do I know it's a unit vector? I'm saying it's a unit vector, but how do I know it's a unit vector?
Its magnitude is 1.
Okay. And isn't the magnitude of this the square of x squared plus y squared plus z squared? And that's why it's 1. Correct. Which means that if you know this gradient vector, couldn't you go to GeoGebra and actually see what it looks like? And what you would get is, when you get a whole load of points, all of them, all the little vectors, 1 unit long. You know how sometimes you can get a vector that's 5 and sometimes it's 2, you know, they're different lengths depending on what the numbers inside them are. But this one would be an example of a vector field, a force field, where at any given point, the magnitude is 1. That can be useful. Don't know what I'm picking here. I'm just randomly picking things, really. I'm choosing this one not because it's difficult. I'm choosing this one because it's easy. It's the fact that it has something else attached to it that's kind of interesting. If somebody asked you to do the gradient of that, I hope you wouldn't even pause. You agree? So what is the issue? Virtually none, except, let me show you what's going on. When I look at this guy in the homework, get a little bit bigger. There. Now in here, you can put your vectors. So I'll make sure I hit my vector thing because I like it that way. I'll do little brackets and I'll write in what we've got. So I had a 2x and comma and I had a -3. Sometimes, and this is, I think, one of these sometimes, you should be able to look at what that vector field would look like. And here are your 4 pictures. Now, I guess if I didn't know how to do it, couldn't I just go to GeoGebra, look at GeoGebra, and then look at the 4 pictures, right? But let's try and do it basically just using this fella. So for any given point in 2D space, there's a vector which is made up of twice the x coordinate, and that's how far you go in the x direction, and -3 in the y. So do you think it's the first one, the one that my mouse pointer is going around, if you can see it? This one here, top left. Do you think it's that one?
The 2x means it will not be constant length. So
Right.
I guess I'm not sure that I want to confidently say it's that one, but it won't be the one to the right, right? Because all of those arrows are the same length.
Okay, so we're going to essentially we're going to go through most of these, probably all 4 of them, and we're going to kick them off for different reasons. So you actually jumped ahead, but that's good. And you're saying this one ain't working because they're all the same length. I totally agree with you. Ain't this one. So then, why is it not this one? Let me phrase it that way.
Well, in the positive x, I'm noticing in quadrants 1 and 4, like, it's like a downward slope, which.
Well, shouldn't a guy in quadrant 1 be 2x and then down 3? Shouldn't it be pointing from top left to bottom right? They should be pointing this way.
Okay, yeah.
And they're not pointing this way. Agreed? Some of them pointing total opposite way. So I'm killing it for that reason, right? Okay, we got 2 guys to go. So we got 2x minus 3. Why is it not that one, the third one?
Same reason. The 2x means their lengths should vary, and they're all uniform, same length.
Okay. So I guess by a process of elimination, it has to be the 4th one. You know, if it ain't the 3, it would have to be the 4th. Okay. So I'm just scrolling down to the next one. Oh, there's the picture. That's the solution. That's annoying. Okay. Done a square root. Let's just return back to the white screen. There we go. So I don't think you're going to find the algebra, the math in this section particularly difficult, right? I mean, okay, maybe a square root thing, but remember symmetry is going to help you out a lot. I'm going to talk a little bit about symmetry. So imagine I had a function and we had X, Y, and Z, right? Symmetry. And I found out this fella. And it was YZ over X plus Y plus Z brackets squared, right? By symmetry then. What would this one be?
XZ over Y, X plus Y plus Z squared.
Right. And the third one?
XY over same denominator.
Right. So if if you haven't caught that, can you see why it's these guys? Right. The X doesn't have an X, the Y doesn't have a Y, and the Z doesn't have a Z, but you can phrase it different ways. It is also possible to adapt symmetry. And this is not as good as pure symmetry, but it can be used. Can you imagine that we had a function that looked like that? Now, it's not symmetric in Z, but would you agree it's symmetric in X and Y?
Mm-hmm.
So if you know it's partially symmetric, you can save yourself a little bit of work, because if you can find f of X, shouldn't you be able to predict f of Y? And if you are comfortable with that, then you should do it. Or if you're not comfortable with that, shouldn't you just do 3 separate partial derivatives? What I can guarantee in this question here isn't that one they're going to be significantly different looking than the other two. Right, the Z one is going to have something that's not quite the same as the others. So always be on the lookout for symmetry, because symmetry is your friend and it allows you to not have to do as much work, right? And we all like that. Efficiency is a good thing. And got a square root. Oh God, this is ugly. But it is the last question, so I guess I should look at it. It's a 3-dimensional function. And it is x cosine of 3y over z. Okay, it's early in the morning. Your brain's, if you're in like my brain, is not up to speed. You have got 3 minutes to find those 3 guys. So I'm letting you go for it first. So go for it, no rush. 2 minutes, 45 seconds.
It wouldn't.
I'm not hearing what you're saying.
The share screen stopped in case you.
Oh, sorry, that was me. It's x cosine of 3y over z. No joy here. There is no symmetry to help you out. But you get all three of them are not totally dissimilar, but there's enough differences to make a difference.
I think I got it.
Oh, well, then you've got a minute. Go and have a coffee, a little sit down, watch some TV, and then come back. If you can do it in a minute. Do you think you got it, Anna? Maybe we don't need 3 minutes then, eh? Okay, we're going to have 3 different volunteers. Who wants the easy one? Which I think is this one. Just shout it out. Anybody? Oh, Travis, go for it.
Cosine 3y over z.
Don't think any are going to argue about that. Would you agree that's an easy one? Okay. Who wants the medium one, which is the y guy? In my opinion, the medium one. Come on, don't be shy. One of you go for it. If you screw up, it doesn't matter. I've screwed up more times than you're ever going to do it.
Negative 3x over z sine 3y over z.
So you take this guy, a cosine gets you a negative sign. That's that taken care of. The 3 and the y disappears in the z. I agree. Okay, keeping the best till last. That one. The z one. Who's going to go for that one?
It's negative 3xy over z sine of 3yz. Z square, 3xyz square.
I think
Any,
it's
is there anything you might want to change? Gee, you get the first shot. There's something that needs to be changed. Come on, don't be so negative
plus,
about it.
it's plus, it's plus.
Did you get my joke there? Don't be so negative about it.
Oh, it's plus, that's right.
Okay, we need a joke before we start the next section, because that's basically that section over with. Are you ready for a joke about Arkansas? Okay. What is the difference between a tornado and a divorce in Arkansas? Come on, say I don't know.
I don't know.
There isn't really much difference. Either way, someone's still going to lose a trailer.
I was thinking like a Wizard of Oz themed joke about like dropping a house on someone, and then I was like, wait, that's Kansas.
That joke died a death. Okay. Do you know that they've discovered that the toothbrush was invented in Arkansas? Do you know how they figured that out? If the toothbrush had been invented in any other state, it would have been called the teeth brush.
It's kind of
Oh,
bad.
that's mean.
Come on. Okay then. What do you call 26 Arkansanians in the same room?
So,
Don't know. A full set of teeth. Okay, is that enough picking on Arkansanians? I've never even been to Arkansas, so I don't even know what the place is like, but I'm assuming it's hillbilly country, but maybe I'm wrong. Is it? Anybody been to Arkansas? Nobody's been to Arkansas. Well, okay. Maybe it's not a very interesting place to go to, I guess. Well, that was one section over with. We are now going to change, change is the right word, we're now going to look at our next section, which is chapter 16.2. And we're going to look at things called line integrals, essentially. Now, notation, how do line integrals get written? Well, you do an integral, you do a C. There are different versions of line integrals because of different nuances on them. One of them might look like this. Right. C will be although it's called line integral, C will be a curve in, how many dimensions is this? In this particular case, it's in 3D. Why is it 3D? Because essentially you have a surface, right? And on this surface, C will be a curve in 3D. And you're going to integrate it over this curve in, well, technically, I should say 2D. My apologies. You can also have, let's see if I pick the way they've written it. Okay, where are we? You can have a curve C, which might be made up of some guys that look like this. That's a line integral. C is your line or curve. Let's see, another one. You can have a line integral. Oops. Which only uses one of them rather than both. That's an example of a line integral. See, there are all sorts of different versions of this guy. There's one called f dot d. Can I find one? F dot dr? Yes, there is. And you can have line integrals that are looking like this. So there are these things out here called line integrals, and we are going to try and show you how you would evaluate a line integral, essentially. And it depends on what you're being asked and the way in which the information about the curve C, right? C is some curve, and it could be 3D. That's why I said 3D earlier on. I know that's the surface, but in this world, it's just X, Y. If you do X, Y, Z, it is in 3D. So let's pick somebody. Let's pick a version where C is given in parametric form. A very common way of describing C, you can describe C like this. Suppose I said C was x equals t squared plus 1 and y equals 3t cubed plus 1. And you can imagine that you had something passing through this. So there's x, there's y, and this fella here, I'm making up, ends up being that. Can you imagine that's C? And you're starting here at t equals 0, and you're finishing up here because that's the direction you're traveling along at t equals 2. And as you travel along this curve, you are passing through various values of x and y, right? And let's say that at these points here, there's a function that's called x squared plus 2y. So at that point, there's an xy coordinate, but there's a value. So can you imagine that all the way along this curve, there's little numbers representing what this is equal to at each of these points. Now, I know there's an infinite number of them, but can you imagine that for every single one of those points, if you thought of plus being up and negative being down, what you could imagine doing, and now it is 3D, is that can you imagine you might have a hill where there's bits above the curve and there's bits below the curve. And what you're evaluating when you get the line integral is the net area. So it is possible for a line integral to be positive, and it is possible for a line integral to be negative. Now, this is not very clear. I totally agree with you, but I'm trying to draw in 2D a 3D thing. So here's the brain. Can you imagine you're doing a curve in 3D space? Sorry, in 2D space right now, right? But that curve in 2D space is now on the floor, right? Every single point in that curve has a value. If the value is above, the wall is above the table, right? If the value of this is negative, it's below the table. Can you imagine that being like a weird fence? Some of the fence is above the ground and some of that fence or wall is below the ground. You are evaluating the net area of that. God, that sounded stupid. I wish I'd thought that sentence better. I'm just trying to get across to you that this is actually something that makes sense, right? It's not just math. These things do actually come out as being useful. So here's my function. Here is this guy. Here is this guy. Suppose I've been asked to do that fella of the function x squared plus 2y ds. And I'm going to use that as the curve and that is the function. So it's going to look something like this. The integral from t equals 0 to t equals 2 of x squared plus 2y, I'm leaving that like that right now, the ds gets replaced by this guy, dt. So in this version, when you see this guy here, it becomes, or gets replaced by, that guy. Now, what do you think I'm going to do with the x's and the y's? They're not going to stay as x's and y's because of this. So what will I end up doing?
Swap in terms in t.
Right. So basically, when you get this line integral to do, can you see what you're eventually going to end up with is a really big, ugly derivative in terms of t. That makes sense? Now, in this case, what's that going to be? It's going to be the integral from 0 to 2, t squared plus 1 squared, added to 2 lots of 3t squared plus 1, square root of this guy, 2t squared, plus this guy's derivative, which is 9t squared plus 1 squared dt. And then, dot, 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 you'd have one of the ugliest integrals in the world. But that's essentially how you would tackle that particular situation. Now, since I just made that one up, I'm not even going to take it any further. I'm going to cheat and use one of theirs, which is a nice, simple one. So our last question for the day is question 1. We're being asked to do this guy. The function is x over y ds. We are given c in its parametric form. X is t cubed. Y is t to the 4. And t goes from 1 to 4. So can you imagine this curve in 2D space starting at 1, finishing at 4, and as it travels along this curve, its value or its height is this expression. So it's going to be the integral from 1 to 4 t cubed over t to the 4 dot square root of this guy's derivative squared plus this guy's derivative squared dt. That's going to be the integral from 1 to 4, 1 over t. This fella is what, 9t squared, and this guy is 16t to the 6.
Professor, I think you forgot the squared on the 3t on the line before.
Oh, yeah, partial derivative with respect to dx, delta x, delta t would be 3t squared.
Oh, I gotcha. I forgot a square here. Thank you. Okay. Let's work on this guy because he is doable.
Oh,
Don't do U subs or anything yet. What would we do next? I want to integrate this. What should I do next?
you could factor out a t to the 4th under the root symbol and then take that out as a t squared. And then that would simplify with yeah.
Agreed? Pull that out first. That's t squared. T squared cancels that. You'll be left with this guy. Now, can you see what's happening here is that you're back to good old-fashioned Calc 2 world. Right, it's a single integral with respect to t. Where do I go next? I don't have enough time to finish it, but at least we can start it. Where should I go next?
U sub with 9 plus 16t squared.
Right, do you see that that's going to work out nicely, but we don't have time to finish? You might get caught up in questions where you do all the clever math and the formula and the plugging in and whatever else you want to call it, and then you get to this line here and you just totally, you know, I don't know what to do. You can't integrate U sub. I tried my U sub and it went nowhere. And, you know, you kind of lose track of what you should do because there are so many different flavors, isn't there, of what can happen in a single integral. I mean, maybe the next time it's an integration by parts, maybe the next time it's a trig identity. So don't let the Calc 2 rustiness make you think you don't know how to do line integrals. You know how to do line integrals, but maybe occasionally you get caught up on the, you know, the details.